Hi, it's Miss Carpenter here at Humble Math. Today in our box, what do we have? We have a photo of my dog. And we have today's socks, which are tacos, because we're going to talk about more stuff on linear relations. And we have a green and an orange little jumpy frog. Okay, let's get started. Oh, and there's one other thing in there. Whoops. I forgot about this. Okay, so there's lots of ways to practice doing your linear relations. And one of those ways, if you like to work with wood, and it's not just in name that my name is Carpenter, I do like to do some woodworking. And here's an example of a dovetail. Well, you can see you have to be able to cut very, very straight lines in order to be able to make a nice dovetail. So that's something you could do. When you're building stuff, you definitely need to use linear relations. My dad taught me a lot about using math in that way. Okay, so we also have this, which wouldn't fit in the box. And this sled is to remind us that when we're talking about slope, if you're sliding down the hill and it's really easy, whoosh, this way, then do you have to put any sort of effort? No, negative, you do not. But if you're pulling your sled up the hill this way, then you have pull, positive slope. Or as some of my grade 9s once said, push potato positive. Okay, so we've got our graph here. We've got our ordered pairs here. And this is a little table that we've decided to use because it keeps everything neat and tidy. And we can see if we always start with the lowest number and go to the highest number. So it gets progressively higher, and this allows us to see the relationship between the x values and the y values and between themselves. So we're looking for patterns. So in this case, we can see a pattern that the x values are going up by how much? So if you can imagine, the frog is jumping by how much each time? Well, you have to add 1. Once again, you have to add 1. 0 plus 1 is 1. 1 plus 1 is 2. I mean, it's not hard. Then, if you're looking at your y values, what's happening with the y values? Well, it's exactly the same thing, right? 0 plus 1. 1 plus 1 is 2. 2 plus 1 is 3. So it's also increasing by 1 each time. So that'll be our little green jumpy frog. Okay, so let's go over here to our graph. And this is our Cartesian plane. And here we can see that this is the way the frog is going to go here, and this frog is going to go up here. Now I use analogies like this, not because I want it to seem like kindergarten, but because your brain loves this sort of thing. It loves to make extra connections. When it does, it remembers things better. So I use these silly little manipulatives to be able to help your brain remember. Plus, it's way more fun this way. Okay, so we're going, temperature is rising. You can see that the temperature is rising. Okay, if we were going to say that this was temperature, would it make sense for both things to be in the negative? I can see a temperature being in the negative, but when in the world would we have the other one be negative? Well, let's have a look at this. If we were going to say that this axis represented time, maybe we could say that we wanted to start on this day, call it day 0, the original day, but that we forgot, oh, we just got some findings that went back 2 days. Okay, well, a day before and the day before that, we could call -1 and -2. So that might be a time, but generally you would start here at 0. I started in the negative because I wanted to be able to demonstrate to you how you can go up, even if you're in the negatives to begin with. Okay, so the other thing is that we talked about begin with B on the y-axis. So if we look at the y-axis, we didn't begin there. And that's the whole point of going through this little exercise to start with. But because we're doing temperature, it doesn't make sense that we would start in the negative days. So your orange is going to represent time. And x-axis often represents time. So that's time. Our y-axis is going to represent temperature. Now, it would have made sense if we had started at a negative temperature over here and then it had gone up, but we have to start at 0 days. Okay, so we're going to go back here. We're going to say our first day is going to be I need a black marker or something other than green and orange. Once again, orange, you glad we're doing math again. Okay, so we're gonna start here. So your X and Y values are here. You start with your day for your X values, and your time is your Y values. Now, generally you would write that up here, but we don't have room, so we're gonna put it like that. So temperature over time. Does it make sense that this is day? I hope you caught that. That can't be the day. What can that be? We said it was time. Well, I suppose we could go day after day, but we're gonna say that this is one day and it's time, day or hour or whatever we decide it to be is fine. But the X, it's not time. Well, we just said it was. So make sure you have these labeled correctly. So this is the time right here, and this here, we can either say it's the temperature or Celsius or degrees or whatever. We're gonna call it temperature in degrees Celsius. Okay, so this is the temperature and it's labeled here, temperature. This is labeled as time here. Okay. When we're talking about time, we use this graph, we can't have these values here. We actually have to start at 0 day. So if we start at 0 day or 0 hour, and in this case, we're gonna do time in hours. And we're gonna say that it's a steady increase in temperature. So every single moment that it is increasing, it's increasing at the very, very same amount. Why that's important is because even if we're not looking at the temperature, I'm not sure why I looked at my pretend watch, if we're not looking at the temperature, after it's 1 hour past, the temperature was still increasing all during this time. If we had looked 1 minute after or 15 minutes after, we would have seen an increase in time. So let's take that 1 hour and split it in half. So that would be 30 minutes right there. At 30 minutes, if this is 1 hour, this would be 30 minutes. Then we would go up here and we would see that the temperature would be about 1.5 degrees Celsius. So you can see how it's important to put all these points. And this is called continuous. Now, can you think of a situation where a graph would not be continuous, where things wouldn't be happening except when you actually had a point here? Well, I'll give you an example. Picture of my dog. If I go to get photographs and I go to pick them up and they say, okay, it's gonna cost you 60 cents each picture. Or in this case, let's make it really easy. It's gonna cost $1 for a big picture like that. I know, isn't she cute? This actually was just a little fun project, and this is an extra copy that was gonna be thrown out. So if I go to get my pictures and they say it's gonna cost you, let's say it's gonna cost you $1 no matter what, even if you don't get any prints. It's just gonna cost you $1 to develop or to put it through the system. And then after that, it's going to cost you $1 for every print. Well, I could say, okay, for one print, at 0 prints, we still have to pay $1. For one print, it was $2 because 1 plus 1. For 2 prints, it was that original price of 1 plus $2 more for 2 prints. But is there any value in between 1 photo and 2 photos? No, you can't have half a photo. You don't go and say, well, I've decided I only want her head. Half a photo. No. So that's a discontinuous one. It's not continuing the entire time. These would be separate dots. So you would only put the dots in that case. So that's one concept. Okay, another thing we need to talk about is this form that we've decided to use. Y equals mx plus b. This is called the slope intercept form. But there are other forms too. We could, if we went way down here, we could use a function like this, where we still have our mx plus b, but we say something is a function of x, which makes sense because whatever you have for your x and y value, they're going to be related. There's a relationship there. And then this last one is standard form. So those are just some other forms. We're learning about the slope intercept form, and there was a mistake over here, so I hope somebody caught it. We call it that because we use the slope and the intercept on this side. Did you notice anything here? It's called the slope, not the internet form. It's called the slope intercept form. So slope, which is M, and intercept, which is B. So that's our MB form. Now, I just said that if you wanted to use this function notation, you could use it because one of them is dependent on the other. So let's try and figure out which one would be our independent and our dependent variable. So we've talked before about how the x and y are variables because the word vary means to change. So these are the things that can change. And as you see, when x is 0, y is 1. But when x is 1, y is 2. So they change. Those values change. And that's why in our form up here, this slope will remain constant. The beginning will be the same no matter what, but the x and y values can keep changing. That's going to be important later when we actually get to practicing. Okay, so again, we're going to come back here to our ordered pairs. Remember, it's x, y with those brackets, which means the order matters. So our x value is 0 and our y value 1. What does this mean? Well, in this case, it means our time is 0. So when we first start, the temperature is what? It's 1 degree. So we go over on our thing here, and where is the B beginning? It's 1. Actually, let's do that in pink because our brain loves to categorize things by color. So that is 1. Our B is 1. What about our other values? Well, we know that x and y could be any of these, but what about this M, this slope? We talked about how it's positive because you're pulling your sled up the hill. If we were going this way, it'd be negative because you're just slipping down the hill. But if it's positive, what does that mean? And we talked about it being steep or a gentle slope. Well, how can we find that? So there's different ways to find it. One of those ways is to just look at our ordered pairs and see what that difference is. So because slope is the rate of change, it's how much things are changing. So with a linear relationship, it's changing at the same rate every single time horizontally and another rate that is constant vertically. So another way to write change in math or physics or other notations is to put a triangle like that. That means change. So the change in the y values divided by the change, in the x values will give you your slope. Remember, we're looking for the rate of change. We're looking for the rate of change. So how much is it changing on the y divided by how much it's changing on the x is going to tell you how steep our line is. Okay. So back to talking about a function. Well, which one is dependent on the other? If I'm talking about our y values, that's temperature. Is temperature dependent on what time you're looking at, or is time depending on what temperature you're looking at? An example I like to use with my students is that if I say that sunshine makes me happy, then I would say my mood is dependent on the weather. So my mood would be the dependent variable, and the weather would be independent of my mood. And what does that mean? Well, if I go outside and I stub my toe and I'm now angry, that doesn't mean we're going to have thunder and lightning. The weather is not dependent on my mood. So what is dependent here? So what is the constant thing that is happening and will not change no matter what? Well, time. Time is one of those things. The time is ticking along here, whether or not we're measuring it. But if we use the time and we say, okay, at 2 hours, the temperature has changed. The temperature is changing and it's dependent on the time. So our x is going to be our independent variable. And that's why I left a little extra space here. Independent. And this is going to be dependent. Depending on what time you look at, you're going to have a different temperature. Okay? Okay. Let's take a couple of values and figure this out. So does it matter which values we take? It doesn't matter at all. What is our b? Our b is 1. How do we know that? Because when we're looking for the y-intercept, or our beginning, x must be 0. So that's our y-intercept right there. And we can see that because it intercepts the y-axis right here. So how much is it going up and over? Well, we have to talk first about how much it's going up or down. In this case, it's going up, as you can see. Because we always read, just like we read books in English or French or many other languages, we read from left to right. So we're reading, first of all, from left to right. So we look, is this line going up when we're reading from left to right? It is. So again, it's positive and we're going up. So how much are we going up? So we have to choose 2 dots. So I'm going to choose this one and this one. So let's talk about what the ordered pair is here. First of all, the x value is 1 and the y value is 2. So it's that one. And on this one, the x value is 3 and the y value is 4. Okay, so we have 2 ordered pairs. So what is the change in y? Well, if you take the higher one and you subtract the lower one, you're going to get a nice positive number for change. So how much did the y change? Another way to do it is to start at this point right here, our 1, 2 point, where y is 2, and say how many jumps to get to that next point. How many jumps? 1, 2. Okay, so we can either say, physically look at the graph and see that you went up 2, and that was the change that happened on the y, or we can say, take the y value and say 4 take away 2 is going to be our change in y. Change or difference is using subtraction. So y is here and here. What is that change? Our change in y is 2. Okay, so our orange frog went up, speaking of mistakes, that was supposed to be green. So our y value, 4 minus 2 equals 2, or our change in y was 2. It jumped up 2. Our x value, it's going to start here at 1, and how far over did it get? 1, 2, right here. It also went 2. So if we look at our x value, we have 3. If we line it up with that, and for the other point, it's 1. And we can see 3 and 1 right there. So let's take the biggest one over here and say 3 minus 1. Now it's totally up to you to decide which values are your second values and which values are your first values. You can't use the 4 from this ordered pair and not use the 3. It won't work. You have to make sure that you're using the same one. So we're saying our 4 from this pair, take away 2 from this pair, those are the y values. We have to put these ones in the same order. So we started with this point right here for the 4. When we do this one on the bottom, we have to start with the same point. We still have to start with that point. So let me just explain that again. Our first point, we're going to call this x2 and y2, and this one x1 and y1. And we're just doing that because this is the second set of values over here, and here this is the first set of values. So we've got x1, y1, and x2, y2. And some people write this formula as y2 minus y1 all over x2 minus x1. And you can also use that as your formula if that helps you. So the change in y over the change in x, make sure you're considering the same point when you're putting it in order. And then you can come up with what your slope is. What's the steepness of your line? So in this case, it's 2, and in this case, it's also 2. So our slope of our line is 2 over 2. And what that means is that you can go from this point to this point by going up 2 and over 2. Because this is the up and down, and this is the left or right. Now in this case, you will notice that this can be reduced to 1, or 1 over 1. Now I always tell my students, when you're doing slope, write the slope in fractional form. So even include this 1. Even though we know that just means this, we don't have to put 1 over 1. The reason I say put it this way is because then you can say this is your rise or fall, and this number is going to be left or right. So if you imagine that you're on your graph and you're trying to figure out, okay, well, where does my slope go? Well, if I start at my first point and I go up 1 and then I go over 1, I'm going to get to my next point. And the same one, up 1, over 1, up 1, over 1. I could keep going, up 1, over 1. Next one would be up 1, over 1, up 1, over 1. Okay? For your slope in this case, it is rise or fall over left or right. And can you imagine if it's going down, we know that these values are negative. If it's going to the left, we know these values are negative. So remember that as we go to the next video to learn how to calculate slope from here.